Alrighty. So last week, or last homework, we talked about magnetic fields, and we didn't really talk any about how they come from. We just said, okay, if somehow you have a magnetic field, this is what happens, right? So what we want to talk about this week is where you actually get magnetic fields. So this is homework 6. And so just a really quick recap last week, we had that if you have a magnetic field, it does nothing to a stationary charge, right? Because we had the force was Q times V cross B. So if a charge either isn't moving or, well, since that cross product has a sine theta in it, if a charge is moving in the same direction as the field, it's like the field isn't even there. It doesn't do a thing. All right. Actually, it's kind of the same thing as far as where do magnetic fields come from. The most common place is charges moving. So the most common source of magnetic field is if you have moving charges. And the law that goes with that is called the Biot-Savart law, which honestly I never remember because you don't use it. There's just like before we had like Coulomb's law where electric field was kind of inverse square, but then that, oh, most of the time you don't actually use Coulomb's law, you can do Gauss's law to find these instead. There's something just like that. The original is the Biot-Savart law, but then here pretty quick we're going to learn an Ampere's law. So Biot-Savart law is right there. So the magnetic field from the moving charge is, U naught over 4 pi Q V sine phi over r squared. So that's the magnitude. If you want the vector version, it's down here. So it's, well, let me erase the arrow. So that's just the magnitude. If you want the full-on vector, you have to do a cross product, which we don't actually have cross products in college physics. So, but just so you've seen it. And does it have it? Good morning. Oh, I guess he didn't want to talk to me. All right. The only thing we're going to use this for, so in principle, if you just have an electron moving out in the world, it creates a magnetic field. That's what this says. When do you, hey, how are you doing?
I'm doing, I guess.
You're doing, you guess? We're talking about the Biot-Savart law. Does that make you excited?
What?
The Biot-Savart law.
I don't even remember that one.
You don't remember that one?
I don't remember that one.
Yeah, that's because we use it for like 3 seconds and then we learned Ampere's law. Okay, so at least for purposes of this class and really for all real world purposes, if you have a moving charge, it's probably part of an electric current, right? So usually charge is part of electric current. So that's what we're going to actually use this for, is like if we have a, okay, oh, gotcha. It's like, dude, he just like walked out. Okay. Was that? No, hey, I can't blame him. I got here and I ran to Mrs. McCoy. She's like, "Oh, how are you doing today?" It's like, well, I have to say this is about the least Friday-ish feeling day I've had in a while. All right. So what we'll actually use this for is if we've got a piece of wire and we just want to say, hey, what's the magnetic field caused by a little chunk of it? That's what we'll use this for. So, how would this change if well, I mean, when you're talking about current, you don't really talk about velocity, you talk about, well, current, right? So, which we did this before. We said when we did the magnetic field on a charge, it was like, okay, V cross B or whatever. But we said if you have magnetic field acting on a wire, what did we do with that V to make it look like current? Do you remember? No? Okay. So remember, and what is current? Current is the speed of charge, right? So it's charge over time. What is V? Well, V is like distance over time. Let me just say D for lack of a better whatever. So if I look at my formulas, I've got this Q times V, right? So if I go Q times V, that's Q times D over T. That's I times D, right? So most of the time, we're not actually going to use the one with the Q and the V. We're going to change them to a current and distance. So you would have B is, I just realized I never told you what mu naught was, did I? Over R squared. And again, this cross product here, if you just want the magnitude, this is distance times, well, this is R hat. So R is 1, so it's just D sine theta. Where theta is the angle between the D, which is carrying your current, and the R, which is the direction to your charge or your point where you want to know the magnetic field. Okay, and let me tell you what mu naught is. Mu naught is exactly 4 pi times 10 to the minus 7th. Oh, whoops. So this mu naught over 4 pi is actually just like 10 to the minus 7th. Make sure there's mu naught. I'm just going to double check to make sure it really is 10 to the minus 7th. But yeah. Oh. Yeah, it's 10 to the minus 7th. That's kind of fun. Let's do that, even though we really won't get to it till a little bit later. But let's talk about it anyway. Does anybody remember what epsilon naught was equal to? Yeah, 8.85 times 10 to the minus 12.
Yeah.
Somebody who has a calculator, punch in 1 over the square root of mu naught times epsilon naught.
Positive 7, right? No, it's still negative.
Negative 7. Get it? Is it?
I got 0.0026.
I'm not even close. Let's see what Cindy gets. What'd you get, Cindy? What? Okay. Let me try. So we've got 4 times 5 times 8.85. I want 1 over that. And then I should have a 10 to the negative. Well, I did 1 over, so it'll be 10 to the positive
shit, I got
19.
something way different now.
18. That, and then I want the square root. Hey, that's what I was
That's what I
expecting.
got.
Hey, that's what you should have got.
Okay,
Does anybody recognize that number?
I do, but I can't tell you what it is. Said it before.
It's very, well, we usually round it off to just 3 times 10 to the 8th. This is the speed of light, which is roughly 3 times 10 to the 8th. So, we'll see why a little bit later. As far as what this mu naught is, well, it's like epsilon naught. I mean, that number kind of measures any material in the world. There's a certain resistance to trying to build an electric field in it. And epsilon naught was that resistance for empty space. Mu naught's the same thing. For any material in the world, there's some sort of resistance to wanting to build a magnetic field in it. And mu naught is that resistance for empty space. So when we do like dielectrics and stuff, then these will change to like mu's and epsilons that you'll have to look up. But basically every formula that we have will be exactly the same. It's just, change all the mu naughts to mu's, change all the epsilon naughts to epsilons, and go from there. Cool. So that's kind of a good starting point. Let's go ahead and